So in this video, we're going to present to you our previous works for algorithm design in the mobile ad hoc networks. And the topics of the slide is called constructing and maintaining a connected K-hub dominating set in mobile ad hoc networks, where this is research that we have done when we were in a national Tsinghua University of Taiwan. Following is the brief agenda above, including the introduction of the background, notations and preliminaries, proposed method, and also some simulation results and the discussion. So for basically first we want to introduce you what is a dominating set and what is a K-hub dominating set and what's the notation and their application for that. All of those topics has and also there are a proposed method that we just trying to put it down below of the slides. First, we want to introduce you the motivations of this slides and what are the motivations of our works. It originates from the mobile ad hoc networks. Those are networks that might comprise with devices either by using Bluetooth or Zigbee or sensors or just laptops. It's a dynamic organizations of network nodes and they're trying to communicate together. So a lot of the issues that has been discussed once this concept has been proposed. But mostly when the things gradually converge to the research issues, it has been discussed for several categories, such as sensor networks that has been used for space exploitation. And also there'll be vehicular networks that has been assigned for the communications on taxis or buses. And even they have some study for observing the moving patterns of animals. So they are like animal interconnection networks that have been studied or traced before, and so on. So the proposed method is this. The algorithm CKTS is we have 6 Ks actually, but it's a periodical and also it is a distributed algorithm because ad hoc networks means that they're trying to pursue a distributed way. That means all the perfect conditions of the centralized algorithm has been uh, tried to dissolve into individual and working independently component. So we want to design some methods so that the individual nodes or the participants they have the basic intelligence or the like basic rules that they can follow, so they could help us to construct it in a distributed way. That means even we do not try to take care of that in a centralized way, the results might still not that bad from what we have expected comparing to the centralized method. So there are 5 steps. The 0 step is that suppose there's a graph and also A is the current node. If there's a neighbor B such that this node A, whose neighbor A is contained in the neighbor B, then we try to set the sequence number of A, which is becomes a number which is not infinity. That means we're trying to let the node A at the beginning set up the sequence number as infinite, but they try to remove it because it finds neighbor B, which can cover it. And after that, there are several subcases that needs to handle when we're trying to discuss with the cases for a distributed manner, because nodes might move, nodes might insert, node might removed, node might switch on and switch off. So there are several subcategories. The first one, CKDS1, is that if this node sequence number is infinite and there's a down number which is less than k, then we try to set up the procedure shrink set. That means the down number, if it's less than k, then it needs to try to find out because there are less than k levels of neighbors that could extend from A. So if we want to pursue for the k-hub, then that would be good. But for the CKDS2 is the rest of the case that happens to be the opposite case, which is for the extend set. So if the sequence number is not infinite, that means the node has been removed previously, and also the down number is greater than or equals to k. That means for those nodes which is outside of the set, they might be too far away, so we try to extend the set to cover those nodes if we can detect the down number for any nodes. Now, for CKDS3 is that suppose these two cases does not exist, but for the case of if A received a wake up message and we use the procedure wake up, that means the wake up is sometimes the nodes they just switch on or switch off due to the saving energy issues of the nodes. If we put sensors over the surface of, for example, Mars or Jupiter's or Saturn's, it might take they might periodically try to monitor the data, but once the data collection is finished, the energy mode might try to restore and also switch off due to maybe the disappearance of the sun or so. So that's why we check the case 3. If A received a wake up message, procedure wake up is executed. That happens is when it needs to be wake up. Now the rest of the two cases that if it detects such node A detects its neighbor B switches off, the procedure switch off is executed. And the fifth case, the last case is that if A switches on, then the procedure switch on is executed. So this is a basic one. We're trying to get this because we want you to have some sense for 6 different conditions, but we will explain that gradually in the later parts of the slides. So the first part is for the preliminary is the one-hop dominating set and a k-hop dominating set. Basically, you can see that from the figure 1. Figure 1a shows that a one-hop dominating set D1. That means for those circles with dots, they try to cover the nodes that's outside of the dominating set, but within the big rounded solid lines of the circle, all the nodes belong to a dominating set. So if we continue shrinking, and you can just by your intuition to see that from figure 1b, shows that this is a k-hop dominating set. What does that mean? That means for any nodes, the outsides of the dominating set, that means for those nodes between the double solid lines, and also for those dotted lines, the circles, any nodes, if they want to find a connections toward the centers of the double solid lines, it need to find at most k steps. That is, from one node move to the other node, then move to the other node. So that's we called about k-hop away. For the two rules from Wu's methods and simple inspiration part, that's the introductions that has been previously studied by Dr. J. Wu from Florida Atlantic University. I think he, starting from 1995 or 1998, he has started this works. And his method was very, very simple and useful, that including the cases is that his philosophy is different from ours. I think his philosophy is like that. If there is a node which tries to figure out the neighboring set of its neighbors, and it finds that its neighboring set needs its help. If node A find that its neighbor B and neighbor C needs its help for connecting, then it's trying to insert itself into the dominating set. So that's what a dominating set method from Wu's method, which is different from our perspective. Our perspective and philosophy is that at the beginning we assume that all nodes that they are dominating sets, and once we found that we can depend on our neighbors, we're trying to remove ourselves. So this is just a philosophy for flipping the nodes from the set, or by inserting that by observation, or actually trying to insert yourself and trying to remove yourself out of that. There are different ways for that. And the reason that we mention Wu's method, not only because that his publication is the most in this field, but also because he his method and our method has been eliminated in our later experiments. So we assume that based on the wireless networks and mobile ad hoc networks, which is different from the Ethernet networks, the Ethernet networks, the topology has been fixed. And you might be able to assume that the safety by those very well tailored designs of the hub and also the real wired lines of Ethernet connection. But for the wireless, there are a lot of things that's unexpected. For example, the nodes, they might move away, and if you want to communicate, they might need waves to communicate, like particles of Wi-Fi or Bluetooth. For those small range is the one. But if it's for those nodes that's outside of the space, the conditions might be even worse. Or maybe for those sensors that has been dive and put on the surface of the straits and so on. Now we propose from the concept levels for the binary relation nodes as follows. The binary relation nodes is a relations that uh, between a parent and a child. So if a child wants to find parents, that means its parent could take care of its child's all neighboring. So that means the child could remove it from the dominating set and just do simple but focused thing. But for those those nodes lie inside of the dominating set, they might have to deal multitasking and also communication, and they might be energy consuming for that. But for those nodes which are outside of the dominating set, they can only try to pass information basically maybe by collecting the sensor informations towards their parents. And they assume that the parents will help them to route the message toward the correct path or targets of that. So the figure 1a shows the sequence numbers of each node. So the DEF, they sort of like lies in the center part of that, but the nodes A, B, C, they are lined outside of the boundary, like those dotted lines. Those nodes between the dotted line and two solid lines, where DEF, they happen to lie in the dotted line, solid lines. So once A got sequence number A1 first, then probably B got sequence number 2, and C got sequence number 3. And why do we assign that? We just give you a concept as parents and child. Now, on the figure, subfigure B, if there's an arrow, that means the starting point of the arrow, it happens to be the parent of the ending point of the arrow. That means node A, they got two parents because its neighbor C and also neighbor B, both of them can take care of all its neighboring set. That means A's neighboring set, BC, could be covered by node B and node C because the node B, whose neighboring sets are D, E, C, A, node C, whose neighboring set are A, B, E, F, and that means, but node A's neighboring set only contains B, C, so that means either node B or node C, they could cover all those neighboring nodes of A. So B could be the parent of A, and C could be the parent of A too. The same conditions we can just randomly pick up. that the node A could be the parent of a node C, and also the node F could appear the parent of C. And why is that? That is because for all those neighbors of C whose neighboring nodes happens to have a sequence number larger than C, that means E and F could be covered by the older neighboring set of E and also older neighboring set of F. And that means how come we don't care about the node B? Because the node B sequence number is 2. And the sequence number, if it is smaller, then for finding parents conditions of this relation definition, we trying to neglect that part because philosophically, if your neighbor has sequence number less than you, then probably that means the sequence number of your neighbor, the neighbor has been removed outside of the dominating set. That means your neighbors might have already found its parents, so that means you probably don't have the obligations to take care of your neighbors. So that's how we define the definition of a relation. The relation depends on the sequence number of your neighbors and also the if your neighbor's sequence number is larger than your sequence number, and you can find other neighbors whose neighboring set could cover all those your neighbors whose sequence number is larger than your sequence number, then you can find them as your parents. That's what it is. So we build a partial set, and this is the measurement of paths that we're trying to find out because we will try to record it and also figure out the k-hub dominating set as follows. The measurement of paths is as follows. If we have from A to G, we have 3 paths. Path 1 is A goes to N, goes to N, goes to O, goes to P, goes to Q, then goes to R, then goes to S, then goes to T, then goes to G. This is a long path that has been labeled as the green path. The path 2 is a little bit different from path 1 because it just skipped the node N. That means the path 2 is from A goes to node N, then goes to H, then go back to O, then go to P, then go to Q, then go to R, then go to S, then go to T, then goes to G. So the only difference between P1 and P2 is that P1 has a node N, but P2 has node H. The P3 is another green path. That is from A to B to C to D to E to F to G. Apparently, you can see that the length of the path P3 is better than P2 is easily because if the path is shorter, then the traveling cost and also the energy consumption, conceptually, it consumes less and its safety is relatively better guaranteed. So we can say that P3 is better than path P2. Now, how do we try to measure the path between P2 and the path P2 and the path P1? For the path P2, because it has some nodes that get closer to the dominating set. So you probably can assume that because of that, if it gets to get closest to the dominating set, then its sequence number might be larger than the relatively far away one. That means that if the node n gets sequence number 0, then it's like that. Now, let's check the subcases of these major algorithms individually. The first one is for the shrink set, then it's the extend set. Then we will deal with the switch on and switch off. The case is first, when all nodes are stable and then. I think when all nodes are stable at the beginning, they were included inside of the set. But then, because of the checking rules, once you found that you can just let your responsibility to be taken by your neighbor, then you can freely choose to claim that you're out of the set and you let your neighbors to take care of that. But what will be the claim procedure of that? We can see this from the figure 6. This is an example of shrinking the dominating set. In A, note A is a non-dominating set, and then in B, note B is removed from the dominating set, and in C, note C is removed from the dominating set. This is just a concept. At the beginning, A found that because its neighbor, B and C, they are connected together, and that means if he can try to find B as his parent and also find C as his parent the same. So A chooses to remove itself out of the set so that he can preserve his energy. And with sequence number 1, then after that, B also found that he can find, or she can find E, node E to take care of that, because its neighbor D, C, and E are connected to the neighbor set of E. So that means B could remove itself and get itself another sequence number, which happens to be a number which is larger than a little bit larger. And then C found that its neighboring sets which has a number which is not like E and F is neighboring set which is E and F which does not have a sequence number, then C choose to remove itself out of the set. So what will be the algorithm? The shrink set algorithm is as follows: that node A is removed from the dominating set first, then the shrink set procedure tries to do the following 2 steps. The first one is that we set that the eta sequence is set to a value which is not equal to infinity and is greater than beta sequence for all v which is in the neighbor of A, but except those neighbor of A whose numbers are infinite. That means we have to choose the sequence number first. So when in the subfigure A, remove it because there's no neighboring of A which has a sequence number less than infinite. Then A chooses the minimal sequence number by default. Okay, so the second step is that if there's no node V in PA minus A such that VA is in R, then A that sequence number is set to infinite. That means this is the further checked conditions. So the parent of A, if A found its parent, except itself, if there are other parents of V that could preserve the relation of that, then A the sequence should set back to the infinite. So the shrink set is just some procedure where the SDS2 procedure is for the case after it set up this sequence. So this is the case when all nodes are stable, and then it's very simple, but they're just handling the cases for exception where we want to shrink it. Now, for what if a newbie joins, and then what will be the case? Then this is for the extend set algorithm. So figure 9 is an example of extending the set. Subfigure A shows that the network before extending the dominating set, and in subfigure B, node B becomes a dominating set and send a wake up messages to node C, and then in subfigure C, node C is still the non-dominating set because EC is in R. That means if there are the case where B actually found that it needs to becomes the dominating set when it joins in, then what will be the case? First, it checks that its neighbor A, which has sequence number less than that. So that means, and the reasons that B choose to insert itself probably because they want to preserve the one hop dominating set. When B detects that its hop number becomes 2, and that's why B choose to insert itself inside of the back to the dominating set, and that's what happened in B. The subfigure, and also after that, it needs to send up the message towards its neighboring set. Why don't B does not have to send to node A because B is a parent temporarily in this temporary structure, so that's why. But if it is for node C, if it's for node C, when node C figure out that B might send a wake-up message to it, then the node C will check up the following information. That is, for all those neighboring B, E, and F, are they can they still cover? I mean, for example, when you check up its parent E and also check up its parent F, because its neighbor right now becomes all those nodes of infinite sequence number. That means it does not have to take care of that. What does that mean? That means right now node C has been surrounded by dominating set. The same thing happens. So that's why in subfigure C, node A still does not also try to insert itself too, because at this time node A and node C they are surrounded by dominating sets, at least from one of their neighbors. So when they need to send something instead of the set, they can easily attach to one of that. But in the subfigure A, because node A is 2 hops away, and when node B found it, node B trying to take care and also take the responsibility of that. Now, what would be the wake up? The wake up is very similar, like what we have done for the extended set. First, if there is no node V in the parent A, except itself, such that all those vertices which preserve the relation of that, then first we try to choose those. The messages that we need to send back, and also we set a sequence number set to infinite. This might be a little bit redundant, but as you can see that when we're trying to emphasize this wake up procedure, actually we're trying to make sure that if it's a K-hop dominating set, and then probably that all of a sudden the changes could make the route very, very hard and difficult, but at least for this posturing ordering, even the sequence number has been changed. We can still try to track by along the sequence number. But if that's true, then we have to make sure that we have to attach to the correct parent. So the structure of that, if you cannot find that, you have to wake up your parents to help you. I guess that's the basic philosophy of that. So we're trying to emphasize this. Actually, the procedure is similar like the extend set. Now for the energy saving issues node may switch on or off. What about the first case? This kind of a case, if you're trying to figure out that for laptop usage or cell phone usage, currently you can find a lot of like charging service that has been set up along the public space. That means the things does not happen too much. But for the issues that if you want to deploy the real sensors along the surface of planets, and the things could happen because we are put all those robots or machines outside of a very very cool environment, and for those cool environment, if we have energy saving issues, the node needs to be intelligent enough to switch itself on and also switch itself off. Just due to the case, for example, if it has to finish its jobs, like collecting the moisture of the atmosphere, or maybe just collected the or do some basic analysis about the component or of a sample. Then it can just switch itself on or off. So that's what we expect for that. Now in figure 11 is an example of switching on of a node E. Now previously the cases was like A connected to node B, and connected to node C, and also connected to node D. But B, C, D, they don't connect to each other. This is conceptual condition. So maybe you can think of that as a little bit flattened conditions where B and C might be, or C and D might be too far away from the conditions, the distance between A and B and A and C and A and D individually. But if E has been inserted and happens to connect it to B and C and D, what happens is that once node E chooses to switch on, then he will have to check that it's neighboring. When E check is neighboring, then what kind of neighbor that node E has? It has node B, which does not belongs to the set, and also it has node C, which are in the set, and also D, node D, which are in the set. But at this time, when E trying to find that B is not in the set, it could trying to check the value that, and E choose to does not try to like relinquish the its rules as dominant set because it found that none of its neighbor can take care of the rest of its neighbors at each other. So that means that you yourself needs to join the set. But then after this step, no matter which sequence number that B is, then because B is not in a set, so B has to receive the wake up message for E. So after checking up the wake up message of E, then at this time B also realized that its neighboring set they could not cover into each other. Previously, B might thought that it's outside of the set and also it only can find the parent. But right now, because it has the two neighbors, they are not connected together, and B needs to take the responsibility to connect them. So that's why B joined itself instead of dominating set. So this is what the figure 11 trying to tell us. Now, it may decide to switch off just because the node they have finished their task jobs. So what then? The case was like that. This triangle-based figure 13 is an example of node E switching off. In subfigure A, node E switches off, and in subfigure B, node B becomes the dominating set after E switches off. Then in figure C, there's a propagations of like a chain effect of that. That node C also becomes a dominating node. What does that mean? At the beginning, previously, we might thought it's just a two-hop dominating set where A, B, and C they are outside of the set, but because the connectivity of D, E, and F, they are connected and they help B, C, and A to share their routing task for that. But once all of a sudden, if E chooses to switching off, then its neighbor D and E, F, and also B and C, they might found it. And what would be those nodes that needs to worry about that? For those nodes which are not inside of the dominating set, I think they need to worry much. So if B found it, then B found that its neighbor C and also its neighbor first B found that its parent is gone. So and if its parent is gone, and if there are uh, if its parent's gone, then first the bee needs to find its parent. And second, if its parent is gone, then probably for those neighboring set of B, for example, like C, then there's no other dominating set nodes or other parent could take care of the node C, its neighbor. So when B found this, B trying to join the dominating set and set itself into infinite number, the same thing happens if C is a little bit slow than node B. Now C found that. The case is that B wake up node C, and the same thing happened is that previously C has a parent F, and also C has a parent E. Now, will the parent of C take care of its own neighbors? No, because F and B is not connected. So C realized that its previous parent F, could not take care of all the condition, and so that's why C trying to join the dominating set. And what happens is that after this propagation, B and C, just because the switch off of the node E and the detection of node B and C, then it results of newly inserted nodes after that. But the propagation trying to preserve that the dominating set are still connected together. So the procedure is easy. The switch off procedure is that node A detects its neighbor, node B switches off, and it's just a simple one-line code. If A dot sequence is less than equals to B dot sequence, and also A dot sequence is not infinite, then we let node A invokes procedure wake up. And you know that the wake up has some propagation. That's why we're trying to emphasize this wake up previously. So it's easy, but all of this figure trying to tell you the conditions that we're trying to handle that as a distributed manner, because the distributed algorithms trying to deal with the case where all nodes they might operate at the same time. Their basic foundation for communication might be the synchronization that has been handled from the MEC level and also from the physical level. But on the network level, when they're trying to handle this routing conditions, they have to handle those. Now, the next slide is that the main theory, if G is connected after any one of the previous 4 operations or a combination, the connected K-hop dominating set is still preserved. We're just trying to show you the partial ordering, also the propagation of that. But if you need more stringent proof of that, please check our thesis in the link that will be described. But later on, we were trying to show you the exactly conditions for our simulation, just trying to give you some sense of what a mobile ad hoc network could be, because it's just a randomly generated one. In this one, it's from 1 hop to 4 hop. At the beginning, from the left and the top of the figure, all nodes, they are dominating sets. But after one round, you can see that all those neighboring nodes has been eliminated, and also they are given some sequence number of that. If there's some sequence number, the hop number of that. It's just a 0 or 1 or 2 hop and so on. So in subfigure B, only 4 to previously there are that many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 nodes. But after one round, there are only 1, 2, 3, 4, 5, 6, 7, 8. That means nearly half of the node has been removed. In subfigure C, only 3 of that. Subfigure D, also 3 of that. That means if we try to do that things gradually, it could happens is that it will shrink and shrink. But you see, how come we're trying to do that subfigure E? Because here there's an additional node trying to attach, which has number 12, ID number 12 attached to number 3. And because it needs to preserve the sequence number at the beginning, it probably has to find out. It will give trying to assign itself a sequence number, and since its neighbor is sequence number 0, so it's trying to give itself another sequence number -1. But because of the -1, and also because it's a new insertion, it needs to wake up its neighbor, and the wake up procedure has some propagation that makes the node 11 finally inserted into that. So this is from 1 hop to 4 hop examples. And what will be our simulation? Our simulation trying to compare ourselves with the Wood master for the K equals to 1 hop, 2 hop, and 3 hop, and 4 hop.
In here, you probably see how come our one-hop condition, if you have read Wu's method, and Wu's method has mentioned about that, one-hop case of Wu's condition is it's trying to remove itself. It's trying to insert itself into the dominant set, and also it has some additional rule trying to eliminate itself. If in the next round it's trying to detect itself, happens to be the redundant dominating set. So that means in Wu's method, there are additional rules that are trying to optimize that, but that might need another rounds of a message exchange. So in here, our k equals to 1, 2, 3, 4 just depends on the number of rounds. Uh, because our method is simpler, the method is that at the beginning, you assume that you are the dominant set, but if you can find your neighbor that needs to can take care of you, then you just give up your condition. And then the second round is just for all those still within the set, they do the same thing. And also the third round and fourth round. So you can see that they just smooth out the number of dominant sets just gradually shrinks. So when the number of the nodes becomes 50, you can find that maybe after first round, there are still at least 40% of the nodes they are within the dominant set. But after 4 rounds, you can see that only 20% of the set has been selected. That means 80% of nodes, their energy can be saved. On the left-hand side is a figure for degree equals to 6, and also the right-hand side is for degree equals to 7. And why do we try to take the simulation for this? Because there are degree 4, 5, 6, 7, 8, 9, 10 cases that has been used by Stojanovich's random density model that has been trying to study for the topological one. And for the topological one, here we just give you some sense about the degree and also the radius condition. This is a additional experiment simulation that we're trying to do by study the mobile networks and also the density issues. It's the some valid sample. We're trying to, for all the possible conditions, to test it a random generated number and also by the degrees. How many mobile network, just the one step of movement, the sample will pass the connectivity. And we found that if it's just for one simple movement of the set, for degree equals to 5, if there are 1,000 randomly generated samples, there are less than 100 of them. They are connected. For degree equals to 6, it becomes more than 200. Degree equal to 7, it reaches half of that. When it degrees reaches to equals to 9 and 10, at least 80% of that, they are connected. How about their diameter? If it's just for the diameter and also the mobile networks, just based on the sample and also the random density models, then what will be the diameter of that? When degree equals to 5, the diameter of the if the graph is connected, then it's more than 20, the diameter. And also, if degree equal to 6, it goes down to 18, and so on. We found that when degree equals to 9, it has reached less than 10, the diameter, and when degree equals to 10, the diameter is less than 6. And that could probably explain the conditions of so-called small world effect. If we just trying to study this basically, Steno Veg, I think it's professor who's pioneering from the mobile ad hoc networks. And his model, by the way, right now we probably have to explain the model to you. It's a model trying to sort up all those edges. If you are given a random graph, first you are trying to find out pairwise length of the nodes. Then you sort up those edges just according to their lengths. And you're trying to pick up those edges gradually, one by one. If degree is equals to 4, and if you have a node 10, then you're trying to pick up 4 times 10 divided by 2. That is the first 20 edges. That's the first 20 edges that are shorter than the rest of that. And if you're trying to pick up the degree 5 and also node 10, then you pick up 5 times 10 divided by 2. That is the first 25 shortest edges of the graph, and so on. So this is how we try to do from the rest of the graph. And also from the right hand side of this is the 1, 2, 3, 4 hop the examples that we trying to provide you. Because previously you have already seen that the topology. If you are given that, how come the 1 hop, 2 hop, 3 hop, and 4 hop domain set could be? And also it based on the diameter. If the diameter I think also is the 5, 6, 7, 8, 9, 10. So the diameter 5 is the blue lines. The diameter 6 is the green line. The diameter 7 is corresponding to the yellow line. And the diameter 8 is corresponding to the orange line. The diameter 9 is corresponding to the red line. The diameter 10 is corresponding to the purple lines. You can see that for diameter 5, that means it's relatively sparse. At the beginning, the one-hop dominating set, if you just randomly generated 100 nodes, it could still more than half of that their dominating set, but its four-hop could be tuned up and also be less than 40% of that. If it is equal to 5 or 6, you can see that if its degrees equals to 5, 6, 7, 8, if its degrees to equals to 8, then at the beginning there are 30 of that, but then gradually maybe around 20 is selected. So that means what? That means 1 hop, 2 hop, 3 hop, and 4 hop. They're gradually decreasing part. If it's for the dense graph, you cannot see that too much. But if it's for the sparse graph, you can see that curve and also how they have reduced that. So there might be some trade-off of it. If you just trying to focus on that. Then also, if just for this random density model, then later on we have to study the relativity of a movement of that. So this is a relatively just because of we only trying to do the sequence of connectivity, not their real exactly sequence. It's just the percentage of the nodes, percentage of the ages that has been inserted due to some randomly generated graph of it. Now, the second part is our simulation for this degrees versus radius. And in this slide is our second part of simulation. After we introduce the degree model, we try to compare the degree model versus the radius. There are several parameters we try to discuss with that. This PM equals to 0.3. That means we're trying to do at least one step of a movement. If it's 0.3, that means 30% of nodes that has been that needs to move a little bit. And the degree is just based on that degree sequence. But also, since this is relatively movement, so there are 4 lines instead of this subfigures that has been described. The line with the square symbols are all those where the movement, if they are randomly moved, their next step has been defined based on the radius. That means in its next step is bounded by 1/4 of the radius of the original graph. And also for the spade, only 1/2 of that. For the triangle, the next step, you can just try to move as far as like the radius has been set up. for the nodes. For the part of this X, it could move even faster. So we were trying to discuss that when 30% of the nodes, when they are moving, if the number of nodes is just increasing, how come the number of change in the nodes will happen? And what does that mean by the number of change nodes? That means the number of nodes that will be inserted instead of the dominant set or be removed outside of dominant set or that part because there's no switch on, it's off. Or you can think of that as a switch on and switch off, but we're just trying to compare after the movement, what will be the dominant set comparing to the movement part and also newly part. And we can see that when if the movement is just around one fourth of the original radius that has been set up, you can see the number of nodes does not increase the number of change nodes too much because they just move a bit less. But you can see even just a slightly change of the radius of the movement to the one half of the original one, after the number of nodes just goes up, it could go beyond the 5. That is, more than 10% of the nodes will be changed of that. That could be the case if you trying to think of that the connectivity and also the exchange of messages within the dominant set of this connected one is important. But if it's just if it's the radius becomes the same and also maybe half doubling, then around 20% of that will changed. If the 20% of the nodes has been changed, and if we consider the conditions to the case where most of the dominants say they might neighbor each other, then that will be some issues. But for on the right hand part, if we're trying to do the degree equals to 10, then it means it's a little bit dense. If it's a dense graph, then no matter which radius part exchange that, the size of domain set, the change of that, we can see that it's not that, the condition is not that diverse. So that means the change of nodes conditions for the sparse graph is an issue, even if we just consider the case of a little bit state of move. And we can also try to show you some other conditions, but instead of this size, we're just trying to show you even one move and also 30% of the move. It will change how much of the set if we insist on the connectivity of the dominating set. And also our algorithms in here, approaching the end of that, we're trying to see that there are still some concurrency issues that we haven't officially tried to discuss with it. And we know that from some officially pioneering Firefly algorithm that has been studied for the sensor networks, we know that they have solved the similar issues in big O of n. So that means for the distributed algorithms, if you want to prove that they are compatible to each other, we could easily just try to apply for the swarm intelligence to our case. But if you are more interested about detail, please check our thesis. So the conclusion and current work is that since we have touched the magic of the randomized conditions in the graph theory and trying to discuss with the case visualized by the mobile ad hoc network, and also that has been put over the case of sensors for Mars exploration or other space mission. And we can see that even if it's slightly changes of the nodes, and also maybe only 30% of that, it will result in the conditions of reconfigurations cost of it. And this condition if it just happens inside of the human world, it could be fixed just by maybe just some traditional ways to fix it. But if it's for some cruel environment outside, in outer space, this optimization requirement might be important because you probably cannot find it very well. This condition could happen when you are traveling outside of fields in the cruel desert and so on. So we believe that our work could help for other study, maybe in the social network, if they think that the set of conditions is also important, for example, for organizing activities or so on. But basically, we are currently trying to adapt our previously mobility model just by the original random walk model to the real conditions that has been inspired by the movie. For example, if you put a census node instead of the tornado, how will you try to manage how this dominating set condition will be? If we just try to study the case that without needing the nodes to be communicated, then that's basic for the scientific condition. But if the conditions has been extended to the space traveling condition, and they happen to trying to organize a troop that trying to travel within, like the movie Interstellar, they're trying to travel within the black hole, then the dominating set might be important in order to preserve how all those ships connect communication. So, but currently we're working on scientific ones that has trying to examine our model and also our simulations for if we put all those instead of tornadoes, and how will those connectivity will evaluate, which might have been studied by the scientific networks of uh, small antennas, like antenna has that have been set up over the trucks, but could still receive the sensors emission signals of that. So if you're interested in our following work, please just keep tracking this channel and our websites. Thanks for listening to this video. This is Hong, presented on behalf of Algorithmic Research Incorporation. Thank you. Bye.